Good afternoon. Welcome to the 5th Pancharatnam lecture. This is a special series of colloquium level lectures in honor of Professor Pancharatnam and illustrious alumni of the Raman Research Institute. Professor Pancharatnam joined the Raman Research Institute as a scholar, senior scholar in 1952. He completed his PhD under the guidance of Professor C.V. Raman. He worked on crystals, optics, and discovered a subtle effect in the interference of polarized light that is now known as the Pancharatnam Berry phase, which is both relevant to classical and quantum optics literature. In fact, when this effect was brought to the notice of Michael Berry, who wrote his paper in the mid-80s, and the paper by Pancharatnam was in the mid-50s, he immediately published an article titled On the Pancharatnam Phase to draw attention to the pioneering work that Pancharatnam had done. So RRI has continued to be very active in this area, and also nationally this is an important area of current research, and I'm really glad that RRI is at the forefront of this area. A little closer to home, and I should say this has been a discovery over the time, so every Pancharatnam lecture my introduction gets a little more elaborate. So Professor Pancharatnam also devised the earliest, I believe, achromatic wave plate for his optics experiments. This was recognized and soon ported to the infrared. And more recently, in an international meeting we had earlier this year, one of the experimenters who is working on cosmic microwave background measurements mentioned Pancharatnam's work as a reference, that they are doing it in microwave waveband also. They're using this whole idea. Professor Pancharatnam passed away in Oxford at a very tender age of 35 in 1969. Okay. So now it's my great pleasure and privilege to introduce today's speaker, Professor Abhay Ashtekar, who is an extremely eminent scientist in the field of gravitation and the quantum theory of gravitation, and rightfully, I would say, is like a living legend in this area of modern gravitation. He is currently Atherton Professor and Ivan Pug Professor of Physics, Penn State, and has held many other prestigious chair professorships, and is also the founding director of Institute for Gravitation and Cosmos, which has made a real name for itself in the international community. Abhay is best recognized for his reformulation of Einstein's theory of general relativity in the mid-80s in terms of what he modestly termed as new variables. Of course, they opened a promising path to quantum theory of gravitation, and Ashtekar variables, as immediately people started calling them, led to a program called the loop quantum gravity approach that has attracted the best minds over past 3 decades and is considered among the leading approaches to quantum gravity, one of the promising approaches. Abhay has many other seminal papers on other aspects of gravitation, and I don't want to spend the entire time here talking about it, but he has worked on very important issues of gravitation, like understanding of horizons and aspects of numerical relativity. And in the past decades, what has been very nice to me, past decade rather, he's been heavily invested in the early universe, which is where there's a lot of overlap of in my personal interest, and he has received global recognition through prestigious prizes like the Einstein Prize. He's a member of the US National Academy of Sciences. He was the president of the International Society for General Relativity and Gravitation. And he also held the C.V. Raman Chair at the Indian Academy of Science right here. Closer to home, he's been deeply involved in the growth of science in India. He seeded activity in India on Ashtekar variables very soon after his discovery, and there are researchers from IUCAA and RRI that I'm aware of who did quite a lot of work, and this opened up this field. And now at this time there are many researchers working in this area in the country. He has served for multiple terms on the Scientific Advisory Committee of IUCAA, and in that role, he provided critical support to bring about the LIGO India project. And I think the community and gravitation committee, as well as the astronomy and astrophysics community, do owe him a great debt for allowing this thing to flower and playing a big role in making it flower. Finally, on a personal note, Abhay has been a great mentor and guide to me. And this is ever since we met first time across the interview table for the first batch of IUCAA graduate students. So Abhay had interviewed me when I first moved into research. And so let me stop here and invite Abhay to give his talk.
Thank you, Taran. It's a pleasure for me to, it's a pleasure for me to give this talk, especially in honor of Pancharatnam. I think, as far as I remember, I heard first from Sam about Pancharatnam and the Bailey's phase and the Pancharatnam phase, that work. But since then, I came to know about his work, which is in addition to what Tarun said, and that has to do with his work on quantum optics, and particularly many of his ideas are at the foundations of the modern work of, for example, laser cooling. And I heard about this in France from Tanujan's group, who won a Nobel Prize for this technique of laser cooling, and he was emphasizing how Pancharatnam's ideas were seminal for that. At first, I thought that I would give a talk which would be more on quantum optics and quantum information, something that I have done recently, and I talked about in Chennai. But unfortunately, that subject is a little more technical, and so at a colloquium level, I didn't know how to make it. So I'm just going to talk about these black hole horizons, which I hope is of wider interest to physics and astronomy community. Okay. So this is a work that I'm going to summarize that has been done by many, many people, not just my work. And the main issue is the following. The black hole, there are many phases of black hole horizon, and the most prominent ones that we know are the ones, for example, this image of the black hole at the center of M87 galaxy. And at the time, at least, this was the most downloaded image on the internet, which is something, says something about our field in this age of film stars and cricket players and so on and so forth all over the world. This is the most downloaded image up here. This is the image. This is the this Event Horizon telescope. This is the image that came from the center of our own galaxy, the black hole in the center of our own galaxy, HGRA star. And this was the one for which half the Nobel Prize of 2020 was given to Andrea Ghez and Reinhard Genzel. And this is the image which is really a black hole merger. It's a computer simulation of a neutron star black hole merger. And particularly the gravitational wave observations that Tarun referred to with the LIGO Virgo laboratories, they have now established that black holes are ubiquitous in our universe. But what exactly is a black hole? What is it that forms as a result of a gravitational collapse and evaporates due to quantum radiation, the Hawking effect? Now, the common answer that you'll find in scientific literature or textbooks is event horizons. But as I'll explain, event horizons are really teleological and have very unphysical properties. Indeed, event horizon may well be actually contained in this room right now and growing. Although nothing is happening in this room really, astrophysically or of significance, the event horizon may be actually contained in this room and growing in anticipation of a collapse that would happen in the center of our galaxy 1 billion years from now. And that is what I mean by teleological. And so it's not really directly physical. And similarly, many of us believe that much of the confusion of the information loss issue in black hole evaporation comes because of over-reliance on event horizons. So is there a better notion of horizons? And the answer is yes, there is. And that has led to many new and interesting insights, and that I would like to share with you. So the plan of the talk is really first tell you about event horizons and their limitations, and then their replacement, which is called quasi-local horizons. And these are, non-expanding horizons that are kind of in equilibrium, black holes in equilibrium. Dynamical horizons are when black holes collide or things are falling into the black hole. And then there is also, thanks to this quasi-local horizon, one can do what is called, what we have been calling gravitational wave tomography. The point is that the horizons, because of the causal structure of space-time, cannot be directly seen. No light actually comes from even the horizon to us. But the horizons, when the black holes collide, they are very dynamical. They grow and so on. And this dynamical process can actually be read off by looking at the gravitational waves that are emitted at infinity. So these gravitational waves provide us an image of the horizon dynamics, much as what we do in standard tomography, where the electromagnetic waves provide us, we cannot see the tumor or something directly or its growth, but we can actually nonetheless picture it, nonetheless see its evolution. And then finally, about black hole horizons. In quantum mechanics, they are really, the black holes horizons, they evaporate. So I'll talk about that, and I'll focus just on the semi-classical regime, and just in one concluding slide tell you what we know about the endpoint. And finally, summary and discussion. So let us begin. So event horizons. What are event horizons? Now supposing I give you a two-dimensional sphere up here, a sphere like that, and supposing I light it, so it's lit instantaneously, then of course there will be light fronts which will be going out, and these are the expanding light fronts. And then of course inside this surface, there will also be light fronts which will be going in, and they are contracting ones. We always have these expanding and contracting light fronts up here. But if in fact you have a mass which is very, very heavy that curves space-time, then what happens is that this outgoing light front gets frozen and it cannot expand anymore. And if it is even bigger, the curvature is even stronger, then in fact the light front both the light fronts might actually be contracting. That means there is going to be a region in space-time which is depicted here in black. That region is not visible to any observer. So here is a space-time diagram, and I'm going to have several such space-time diagrams. Time is running upward here, and space, I can only draw two dimensions up here of space, and this is time direction. And here is a kind of a profile of a star which collapses and forms a singularity, and out far away from the star, light cones, the way that the light propagates, these are the light cones, they are like in special relativity, they are kind of straight up here. But as you come near, the light cones start tilting, and in this region, all the future directed light rays are concentrated, and they fall into this black region. Nothing escapes out up here. And this figure is due to Roger Penrose, and this was used by the Nobel Foundation in its announcement of the Nobel Prize in 2020. Now, a more precise definition of black hole requires what is called as Penrose diagrams. So here what we do is the following. We really are focusing on the causal structure of space-time. So what happens to light rays? That's what we are focusing on. So here is a picture. Again, time is running like that, and space in this case is just one-dimensional like that. Because each point up here is a two-dimensional sphere. So if you like, you can think of it as TR plane up here. And here is a two-sphere that I mentioned before, and the outgoing light rays are going out here. They're expanding, and the incoming light rays are actually contracting, and they are going in this particular way. Now what can happen is that if you have a star which collapses, so the same star which collapses, this is a more accurate description of space-time picture up here. Here the star is collapsing and it forms a singularity, and therefore the curvature is quite strong, and light cones start tilting. And what we can see is that the incoming rays up here will fall into here, outgoing rays will go up here. But inside this region, both the outgoing and incoming, they both fall into the singularity, and therefore nothing escapes at infinity. So this surface up here represents infinity, where the future directed outgoing light rays end, and this will be the past infinity, where the incoming light rays end. So Penrose called it scripti or scry. So this is scry plus, and this is scry minus. Future and past, and future directed light rays are going that way, and the past directed are going that way. So what you're supposed to do is to look at this infinity, and you look at all the part of the space from which light rays can come to infinity. So this is the region from which light rays can all go to infinity. The outgoing light rays will go to infinity. So this is called, this manifold is a full manifold, and this is scry plus, and this is the past of scry plus. And if you remove the past of scry plus from the space-time, we get a region up in this space, and that is called the black hole region. And the boundary of this black hole region, the future boundary of this causal past is called the event horizon. So that is the event horizon up here. And this is a very powerful notion that was introduced in the early 70s and particularly developed by Hawking and Carter and other researchers in Cambridge. And it has been a very powerful notion. And in particular, the event horizons have very interesting properties which caught attention of physicists and mathematicians, and they have developed these ideas in great detail. In particular, one knows that in presence of matter that is ordinary matter that satisfies energy condition, so the energy density is positive and the pressure is bounded by the energy density. The statement is that in presence of such ordinary classical matter, Einstein's equation implies certain laws about how the event horizons behave, and they are called laws of event horizon mechanics. And very surprisingly, they turn out to be rather similar to the laws of thermodynamics. It seems that two branches of science are completely different from each other, but they seem to be similar. So here, in thermodynamics, in equilibrium, the temperature of a system is a constant in thermodynamics. And if you make a transition, so this is the zeroth law. If you make a transition between two nearby equilibrium states, then the energy changes, the entropy changes by this formula, delta E is equal to T delta S plus work done on the system. And the second law says that the entropy of a closed system cannot decrease. Now, in event horizon mechanics, there are parallel laws. Here is the zeroth law, and event horizon mechanics says that in equilibrium, the so-called surface gravity of kappa of the event horizon is constant. What is surface gravity? Well, qualitatively, it is like the little g, 9.8 meters per second squared, the little g on the surface of Earth. And as you know, the little g is not constant. On the mountain, its value on the mountain is different from the value near the ocean. But on black holes, it is constant. If a black hole is in equilibrium, it is constant. The black hole may be distorted because there are matter rings outside. The whole system is in equilibrium. At the moment, idealized situation, nothing is falling into the black hole. So in that case, the surface gravity, even though there may be quote-unquote mountains in the black hole because of these rings outside, the surface gravity is constant. And that is like the zeroth law. And so the surface gravity, which is called kappa, is actually is analogous to the temperature. Now, if I go from an equilibrium state of a black hole to a nearby equilibrium state, then the mass changes, the area changes, but delta m, the change in the mass, is related to the area by just kappa upon 8 pi g times work. And if you compare these two formulae, we already knew that kappa was like temperature, and therefore we are led to believe that area has something to do with entropy. And finally, indeed, the second law here says that the entropy of a closed system cannot decrease, and the area of these black holes cannot decrease. So there is a really completely unexpected similarity between these two branches of physics. Neither knows anything about the other, and therefore this really acquired great attention. And then Hawking's discovery of black hole evaporation really was inspired by this close resemblance, and that gave precise meaning to what is the temperature. And for that, you do need quantum mechanics, you do need h bar to insert in this formula. The formula is as it is, but it is really kappa, h bar times kappa. That has a time divided by 2 pi, that is a connotation of temperature, and area divided by 4 gh bar, or area divided by 4 Planck length squared is like the entropy up here. So this is very attractive, but the event horizons have serious limitations. First of all, I just already mentioned to you that there is teleology. And this idea that the event horizon may be forming in this room and growing is really true. I mean, it's the exact solution of Einstein's equation discovered by the Indian relativist P.C. Vaidya. And here what one does is one takes a null fluid, and null fluid is falling into the black hole, is falling in and is creating a black hole. So instead of star collapsing, we're going to collapse of a null fluid, and because it is null, it is coming in from this past null infinity, and it is falling and then forms a singularity. And again, what you see up here is that here is a null infinity, you look at its past, from here the signals can escape out to infinity, and therefore this is the black hole region that would call up, we'll say. And then at the moment, ignore this, just look at the event horizon, and the event horizon is the boundary of that. Now, before the shell falls, space-time in this whole region is identically, is really flat in this region. So it's just Minkowski space, like in this room. And yet the event horizon is forming and growing because it knows that there's going to be a collapse, and therefore it has to meet the final Schwarzschild event horizon, and therefore it's actually growing. So this is the teleology that I mentioned to you before. And therefore, to know if a space-time admits an event horizon, we need to know its entire future evolution and asymptotics, because, for example, we need to know where null infinity is, the past of null infinity, etc. And it cannot be used in numerical evolution. For example, in numerical relativity, one wants to have two black holes, one wants to evolve them, but if I don't have the entire space-time, I don't know what the event horizons are. So I cannot characterize this black hole by their event horizon. Only at the end of the evolution, I'm able to trace back the event horizon. And then the notion of SCRA is too global. This is qualitatively different from its role in the gravitational radiation theory, where it is used to specify the boundary conditions only. And that is kind of what we do all the time. For example, Maxwell theory and so on, we say things fall like 1 upon r, 1 upon r squared, and so on. That is perfectly fine. But here, because we have to look at the entire past of SCRA, the notion is much more global. And there are analyses, for example, a very beautiful paper by Peter Hijack already in the 70s, which showed that he constructed some models of black hole evaporation and showed that if you just change the space-time geometry in a tiny neighborhood of this the singularity, which you would expect would happen because of quantum gravity effects, that you can make this event horizon completely disappear. And so therefore these event horizons have these properties which are not exactly physical, and therefore is there a better replacement? And the answer is yes, and these are the quasi-local horizons, and I'll spend a little more time on this notion up here. So the main idea is the following. Just a while ago I mentioned to you that you can consider, I can light a light bulb and there will be an expanding light front and there will be a contracting light front. If gravity is sufficiently strong, so the expanding light front just is frozen, it's not expanding, its areas remain just the same. Okay? Then that is called a marginally trapped surface. The area of the light front is frozen, it doesn't change at all. And it's marginally trapped because light is trying to escape but can't quite make it. If you are inside that, then the expansion of the light front, both light fronts is negative, both light fronts are contracting, and that is the black hole region. And this sort of is the boundary of that region up here. So these are called marginally trapped surfaces, and these are two-dimensional spheres. And here is a picture. For example, you may have a marginally trapped surface like that, and here I got the two null vectors, the incoming one, its expansion negative, and outgoing one. Normally it is positive, but on this surface, you cannot see that, but on this surface, the statement is that it will be 0. And now what you can do is, you can take this marginally trapped surface on which light front is frozen, cannot expand, and then we can just let the time pass. And when time passes, you can stack these marginally trapped surfaces on the top of each other, and you will get a world tube, so to say, the time evolution of these marginally trapped surfaces. And that is depicted here by this surface, and it's called H for horizon. It's a quasi-local horizon. And that is the main picture that we got. We can just talk about marginally trapped surfaces, and there's no SCRA, there is no null infinity, there is no past of entire space-time. So in this room, for example, there is no marginally trapped surface. So I can be assured that in fact I don't have a quasi-local horizon here. Now, quasi-local horizon is just a stack of these marginally trapped surfaces, or if you like, a world tube of these marginally trapped surfaces. And this is what is used in the binary black hole simulations. What people find at the initial instant of time, they actually find the marginally trapped surfaces, two of them for the two black holes, and as time evolves, these two marginally trapped surfaces evolve, and they coalesce, and they form a single one. And then you've got a single black hole that is formed by the collision or coalescence of these two black holes. Now again, another great Indian contribution, and that is due to Amul Kumar Rai Chaudhary this time. He has an equation which tells you what happens to this geodesics. You know, they can be null, they can be time-like, but let's look at his equations for the null geodesics. If you use these equations for null geodesics, then that has some implications which are very extraordinary. Namely, let us consider the situations where we are likely to encounter these horizons. First of all, let's look at the binary black hole merger. So in this case, you have got two progenitors, they coincide, and then I got a final final black hole, and that has a particular horizon, the quasi-local horizon, in a binary black hole merges in classical relativity. So this is an example, and in this case, what happens is that there is a flux of radiation into the black hole, and then its area increases. So the marginally trapped surface up here instantaneously is frozen, but as you go along, instantaneously the area is frozen, but as you instantaneously, not its area, the area of the light front up here, this, if you just move it slightly in this direction, the area would be the same, but the area of this surface up here is actually growing. So again, if I go a little bit future, cannot reach there with my height, so if I go to a little bit future up here, again I'm going to have the ln, and the expansion along L direction is 0, but this is not quite L direction, and therefore in this direction the area is changing. But if I were to go slightly above here following the light ray, I will find that the area doesn't change. Similarly here I will have L, and the area there would not change. So the statement is that in this case, this surface is what is called space-like. So in other words, the metric that is induced here is just positive definite, like in ordinary space. For black hole in equilibrium, the flux into the horizon vanishes and the area remains constant, and then this horizon is a null surface, three-dimensional null surface, and during black hole evaporation, the flux into the horizon is negative, and the area decreases, and this horizon is timeline. If the area is changing, like in here and here, the quasi-local horizon is called dynamical, and if the area is constant, the quasi-local horizon is called isolated. And there is no teleology, there is no dynamical horizon or an isolated horizon in this room that we are sitting in. So here is the Baida collapse. Again happens. So what happens is that if you look at the marginally trapped surfaces, in this region a marginally trapped surface forms inside, inside the matter. So in this region is Minkowski, there is no marginally trapped surface. But in the matter which is falling in, the marginally trapped surface forms, the dynamical horizon grows, and then finally when the matter stops, it becomes null. Black hole is in equilibrium, nothing is falling here, and here then it is a Schwarzschild black hole in this case. In this future region, it is exactly the Schwarzschild geometry. In the past region, it is just Minkowski space geometry, and the two are related to each other by dynamical region where things happen and the area of the dynamical horizon grows. Here it is dynamical, and it joins on to isolated horizon, which is also the event horizon of the Schwarzschild black hole. Now, let's look at dynamical horizons first in classical general relativity. So this is a space-like surface, and it is a three-dimensional in space-time, and possibly it has boundary. So for example, in our last picture up here, the dynamical horizon basically starts here and ends here. So it has boundary in both places up here. Here the area is 0, here the area is equal to the final Schwarzschild, namely its radius is going to be equal to 2m. So 4 pi times 2m squared will be the area up there. So it grows from 0 to this. The event horizon is growing even in flat space. Dynamical horizon doesn't exist in flat region of space-time. Okay. So now, what happens to the laws of black hole mechanics and so on? Do they hold for these quasi-local horizons? Now, a dynamical horizon to begin with, as I said, is a space-like three-dimensional submanifold, possibly the boundary of space-time, and it is foliated. That means it is sliced by closed two-dimensional surface, so for which the outgoing null expansion is 0. So the outgoing null rays, their area doesn't change along the outgoing null rays, but for the incoming one, the area is actually negative. And the standard energy conditions hold. Matter is assumed to be the classical matter. Now, the most striking result about event horizons was Hawking's famous theorem, which says that the area of cross-section never decreases if the energy condition holds. But one can never hope to relate this increase in area with any physical process. We just saw in the Weidner space-time up here, this is just Minkowski space, and the area of the event horizon is increasing. Nothing is happening here. For 1 billion years, nothing is happening here, and yet the area is increasing. So you cannot hope to relate this increase in area with any physical process. Situation is very different for the quasi-local horizons, for the dynamical horizons, and this really follows from very beautiful interplay between geometry and physics. These are equations which were discovered in geometry, discovered by Gauss and then Codazzi, some centuries ago. They are applied in the context of general relativity, and you find that the change in the area of the dynamical horizon, so this is the area radius, so 4 pi r squared will be the radius for a cross section of a marginally trapped surface, R2, second one, and this is the one, earlier one, R1, and the difference between them is given by formulae. This is the stationary tensor of the matter which fell in. So this is the matter energy flux, and this is a quantity which is positively definite. It has complete geometrical meaning. This is shear, and this is angular momentum information in it, and this is therefore the gravitational energy flux up here. So the area changes of course it always increases. We see it explicitly, but we also have an expression by how much it changes. So it is related to a physical process, namely it changes because gravitational waves are carrying energy into it, that is the second term, and matter, may be falling into it, and that is the first term up here. And then this is the second law. What about the first law? The first law, remember, was delta m is equal to 1 upon 8 pi j kappa delta a plus this is the work done, the angular velocity of the horizon times change in the angular momentum. This also follows, but in fact, we have something better. In the case of event horizons, you have to have two equilibrium situations. Here we don't need equilibrium situations. I can have dynamical situations. Things may be actually falling into the horizon, and I can go from one instant of time to a nearby instant of time and get this law. And therefore, the first law and the second law are actually valid for dynamical horizons in a much more strong way. What about the 0th law? The 0th law said that the surface gravity is constant, but that referred to the equilibrium situation only. And therefore, we can ask if the horizon is isolated, so nothing is falling into it, it's not growing, its area is constant, and therefore it is null. In that case, do we have the analog of the 0th law? So let's understand this. So first of all, there's a notion of non-expanding horizon. It is a null three-dimensional manifold such that the expansion, the outward light front is frozen, and an energy condition holds up here. Now this immediately implies that the intrinsic metric on this three-dimensional surface is actually time independent, and therefore the area doesn't change in particular because the intrinsic metric is time independent. And we also have a space-time derivative operator given by the space-time metric, four-dimensional metric, and that induces a natural intrinsic derivative operator on this isolated horizon, on this non-expanding horizon up here. Now, if you have non-expanding horizon, which just means that the expansion vanishes, that's the only thing that one is asking here, and the surface is null, then what we already know that says that the intrinsic metric, intrinsic geometry of the horizon is time independent. It may be distorted, but it's not changing in time. But then in addition, the intrinsic derivative operator is also time independent, then we say that we have got an isolated horizon. And these represent horizons in equilibrium. And on every isolated horizon, the 0th and the first law hold. The 0th law in the sense that surface gravity is constant, and first law in the sense that if I went from one isolated horizon to a nearby isolated horizon, so this is like for the event horizon, it's a passive version, one equilibrium state to the next equilibrium state, then the first law also holds. But this is true even when the black hole is distorted because you have got matter rings outside. And we know explicit solutions where the horizon geometry is distorted, but the surface gravity we know is constant. Now, if a black hole is stationary, that is, if you have got a symmetry, time symmetry, that the entire space-time has actually time symmetry, it's called stationary, then the event horizon of that black hole is an isolated horizon. And then the familiar examples are Schwarzschild and Kerr black holes, where the event horizons are isolated horizons. These are the familiar examples. But isolated horizons can also exist in non-stationary spacetimes. You may not have any time-like symmetry. And an example is by a multi-black hole solution that was discovered by Castor and Treschen. There are multiple black holes, but they are held in equilibrium in the sense that they are not falling towards each other because they're charged, and so the gravitational attraction is balanced by the charge repulsion, and they are in a positive cosmological constant space-time, which is expanding. So there is also cosmological repulsion, if you like. And these forces just come together in order to hold the black holes in equilibrium. But still, in this space-time, there is no killing vector field. There's no time-like symmetry in the entire space-time. Yet there are these horizons, and we know that there are black holes because of that. And there is another family of solutions called Robinson-Trautmann solutions. They actually have radiation in them, but none of it falls into the black hole, and therefore, again, we have got isolated horizons. This is quite an exceptional case. It's not a usual case. Do you have a question? Yeah. Yeah. No, good, very good. So thank you. So R1 and R2 are just two marginally trapped surfaces. So dynamical horizon comes with a foliage. Please stop me, ask questions. Dynamical horizon comes slicing. So I'm just looking at one and the other. So the question is about, do I need orientation? What do I mean later? So what you have to do is to look at the preferred null vector L and look at its projection into the horizon. And that gives you, it's a space-like vector, and that tells you that what you mean by a time evolution in that case. So it's along L, all these statements. R2 is quote unquote in the future, even though the projection is space-like, we say along L, it is in the future. Okay. All right, and then finally, dynamical and isolated horizons are widely used in mathematical, in geometric analysis, for example, in mathematical literature, and also especially in numerical general relativity. That's what people use when they talk about black hole collisions and so on. Initially, in the distant past, the two progenitors are very far from each other, and that literally the initial data is taken to be that given by the isolated horizons. And the characteristics are measured using the isolated horizon, like the area and mass and angular momentum is. And then as they come closer to each other, they get distorted, each other's attraction. Some radiation may also fall in. It's very weak in the post-Newtonian approximation when they're just going around, where they're very far away. But close to merger, then you need full general relativity. And again, what we have is this isolated horizon become dynamical. There are two dynamical horizons, and then they merge and form a common horizon. And that is a common horizon that falls. Just for a few experts who are in the room, there is a very astute and beautiful and detailed work done by Badri Krishnan and his then student Pul Kolb, which actually traces what happens to these individual horizons and sees how they merge with the final dynamical horizon. And it's a really very, very tricky and beautiful work, because previously people thought that these horizons just jump. They don't jump. They actually join on continuously, not smoothly, but continuously. Okay. So this is the statement about the dynamical and the isolated horizon. Now what we want to do is to capture the dynamics, the change and such thing of these horizons. So for example, I just keep saying that you have got these two black holes, they come near each other. As they're coming near each other, in the distant past, they look like Schwarzschild or Kerr black holes. If they're spherical symmetry, no angular momentum, they'll be like Schwarzschild. There's angular momentum, they will look like Kerr, isolated horizons. As they come closer, they're going to be distorted and so on. How can I measure in an invariant manner what these distortions are? When they collide, again something happens, and then finally it settles down to a Kerr black hole in the distant future. But when they merge, the structure of the dynamical horizon is extremely complicated. Very quickly it settles down to Kerr, but it's extremely complicated. And I can see it in simulations, but it's all coordinate dependent. I do a simulation, I use a coordinate system, I use a slicing, I use a particular numerical code, and Bala does another simulation, he uses his code, he uses his slicing, he uses his coordinates, and I don't know what the relation is between him and me, right? I mean, he sees some distortions, I see some distortions. What is the invariant meaning of this? And the beautiful thing is that for these quasi-local horizons, you can capture in an invariant manner these distortions in shape and also distortions in the spin structure. In this dynamical situation where the two black holes are colliding, it's not that the black hole is just spin is pointing in some direction. It's really rapidly rotating. It's all kinds of things are happening there. How can I capture that, right, in an invariant manner? So what happens is that we can define so-called multiple moments. And this is something you can do for dynamical horizons and isolated horizons. You cannot do it for event horizons, basically because event horizons do not have a natural slicing. Here we've got a natural slicing for the dynamical horizons. So what is the idea? So the goal I already told you, to extract physical properties of black holes in an invariant manner. So strategy is like in electrodynamics. In electrodynamics, in flat space-time, just one second. In flat space-time, we've got charge and current moments, and they can be used. These are just a bunch of numbers now, right? QLM and JLM, and they characterize a source. For example, I may have thin shell, and I may have some charge distribution, and I may have current distribution, and these moments will tell you. These are just numbers, right? So you can get numbers, and I can get some numbers, and I just say, are the two numbers the same? If they are the same, then I will just say that the current distribution and the charge distribution is the same. Please.
So you said that there is a natural choice of foliation. Does this mean that somehow that, especially in complicated spacetimes, dynamical spacetimes, there's no natural choice. So what?
No, it's a foliation of just the horizon. I don't need outside foliation.
Right. So what? Yeah. So maybe I missed that. I didn't understand what exactly what determines that choice of foliation.
So a dynamical horizon is a stack of these marginally trapped surfaces, and this marginally trapped surface gives me two sphere, then the next two spheres. So every dynamical horizon is foliated by marginally trapped surfaces. There is a unique one. Yeah, this is a theorem that Greg Galloway and I proved, that the foliation of the thing is a unique one. And then in numerical simulations they find, right? In numerical simulations they do use slicing in entire space-time, but then they finally isolate the one surface, the space-like surface. The foliation goes out here, but I isolate one surface, and then I get this foliation. Yeah, the foliation is unique, is a theorem of Greg Galloway's and me. Okay. Yeah, thank you. So the strategy is, as in electrodynamics, we just have this bunch of numbers. So can we get the shape, the complicated shape of the horizon encoded in some numbers? And those of you know some differential geometry, you know that if you're given a two-manifold, then its shape is encoded in the scalar curvature. So from the scalar curvature, can I extract some numbers in an invariant manner? Because I don't want to tell you the value of the scalar curvature in some coordinate system. And the statement is that you can do that. And the point is that you can do it in an invariant manner. I don't have time to explain that. I'll be happy to explain the questions period up here. And so we can do the same for the horizons. Oops. We can do the same for the horizons. Now, on the horizon, of course, in general, there will be no matter, but we can use the geometry of the horizon to assign to it invariantly defined shape moments, which you call I, shape is I up here, Lm, and the spin moment, which is angular momentum, therefore LLM. That encode the rotational state, and these encode the distortions. These really are constructed out of the scalar curvature, and these are constructed out of what is called rotational one form, which is invariantly defined on both dynamical and the isolated horizons. And they represent effective mass and angular momentum multiples, if you like, of the horizon. You just have to multiply them by some dimensional factors to get mass and angular momentum multiple. And now, if you have a dynamical horizon, when the two black holes collide, the dynamical horizon has a complicated shape and so on, but it's not coordinate dependent. I can calculate these multiple moments, and I see that they are very, very far from Kerr multiple moments. And yet, as time goes on, the Kerr it settles down and becomes Kerr multiple moments. So this is another mystery and this beauty of black hole, subject of black holes, right? That somehow in the beginning they are very, very complicated, and yet very soon they settle down to some simple structure up here. So I just continue here. So black hole uniqueness theorem tells that the dynamical horizon always settles down to a Kerr isolated horizon in the distant future. The dynamical horizon multiples have a complicated structure at the merger, and they undergo rapid dynamics and settle down to rather simple Kerr moments, which are completely determined by just two numbers. So I got infinitely many numbers here, and they are just functions of these two numbers, the total mass and the total angular momentum. And in numerical simulations, these functions provide an invariant characterization of this fascinating dynamics. And this has been done, as I first mentioned, Poukolb and also by Booth And then in this country, there was sort of a nice, in ICT, yes, in fact, by Prayush Kumar and Neil Kera and various other people. And this cannot be done for isolated horizon, for event horizons. Okay, now this is a fascinating new subject, which is still being worked out in all the details, but the first results are clear. Namely, what we want to know is, well, common horizon is formed and it has a complicated structure, right? Okay, but I can take numerical simulation and I can work it out, if you like, by looking at the horizon. But can I somehow read off that structure by seeing what goes on far away detector? So here is far away null infinity up here, so my detector may be somewhere here, and here is a black hole. So here is a dynamical horizon that is formed, and then it's sort of, it's highly distorted, and then at late stages, it can be approximated by perturbed non-expanding horizons. For those of you who are experts, this is really the non-expanding horizon together with quasi-normal modes of the black hole. And can I check, can I deduce this evolution by looking what happens to the waves? I got waves here, and is there information in the waves from which I can read off the horizon dynamics, even though I cannot look at the horizon, even though I don't have direct knowledge of the horizon dynamics itself? And the answer is yes here. So numerical simulations, okay. Dynamical horizons are not directly observable. Observers in the asymptotic region cannot receive signals from the dynamical horizon. Still, can we perhaps image the evolution of the multiple moments of these horizons from gravitational waves which are outgoing up here, and then we can. And this is the gravitational wave tomography to image the horizon dynamics. So numerical simulations show that a few cycles after the common horizon forms, it can be approximated, quite well approximated, by a perturbed isolated horizon with infalling radiation, which is represented by linear combinations of so-called quasi-normal modes, and they have very distinct, discrete, complex frequencies determined by the final Kerr black holes. This quasi-normal modes also has a great origin in India. It was first were discussed by Vishweshwara, who used to be here for many times, and they were worked in great detail. They were brought to forefront by Chandrasekhar. A lot of his later years papers on Kerr black hole and working out the quasi-normal modes and so on, and he sort of revived the interest. I mean, people knew about it, but people were not really that interested. But with Chandra's work, really quasi-normal modes were computed in great detail, and there is a cottage industry associated with quasi-normal modes now. Okay, so the statement up here is the following. Given a waveform at infinity, so this is what the detectors see out at infinity, one can extract gauge invariant information in it and transport it to the horizon using Einstein's equations. So Einstein's equations are the ones which are enabling you to read off what is happening here by just looking at what is happening here. And this is very amazing because it is a highly nonlinear phenomenon and such thing, and we can do it. And again, those of you who are sort of experts here, really the multiple moments, in the simplest case of the non-rotating black holes, the evolution of multiple moments here can be read off by looking at the evolution of supermomenta, the BMS supermomenta at Scry. So there is really observables that can be read off by gravitational wave detectors. They directly tell us how the horizon dynamics, how the horizon settled down to its final state through this non-trivial dynamics. And so the statement is that basically that there are many conceptual mathematical subtleties here, but they have been handled, and the upshot is that there is a path to create a movie of how dynamical horizon shape and spin evolves, knowing only the waveform at infinity up here. This program has been completed with the final remnant in Schwarzschild. An extension to Kerr is more involved, but there is no conceptual issue, but there are many, many technical issues that still need to be involved. Now, just again for some few experts in the audience, let me say that there is a general perception that yes, that horizon when it's formed, it is very, very complicated, but then it radiates away its complicated structure and settles down to Kerr horizon in the future. That's it shades its hair or something. That's what people say, and that is incorrect because nothing can escape from the horizon to infinity. Okay, you cannot really causally it is impossible. Rather, what is happening is that there is actually a pool of radiation just outside the common dynamical horizon, and there are correlations there. Some of the radiation goes out to infinity, some of it falls into the horizon, and it is the radiation which falls into the horizon that removes all the crinkles and the creases It is like an iron, if you like. The radiation which falls out irons out the horizon and makes it final curve horizon up here. So it's really a very beautiful thing that is happening. It's like little sprinkling of radiation which straightens out and makes it very simple and beautiful at the end of it. Okay, so this is really the, now I just want to change the gear completely and talk about the black hole evaporation. So where are we? I told you first about the limitations of the event horizon, and then I told you about quasi-local horizons, and there are numerous applications, and these are ongoing applications to classical relativity. Then we want to change gears and talk about black hole evaporation for a few minutes. Okay. So I think most of you know that this was discovery in the mid-70s by Hawking, that although black holes are black, they don't radiate anything classically. Quantum mechanically, there is a radiation, and in fact, this is the famous Hawking radiation. So since they are radiating, so supposing I got a black hole which is formed like here, the black hole is formed up here. This is a stellar collapse. It forms a singularity, and this is the event horizon. This is like the very first picture that I had shown for the stellar collapse. If I had a only classical physics, then this horizon exists forever, goes on like that. But because it is radiating, the black hole is losing its mass. Therefore, the horizon shrinks. And finally, the black hole mass has completely gone away, and therefore the heuristic picture would be that it would no longer exist. So the horizon, instead of continuing forever, it is really shrunk and gone away. So in the distant past, this is a constant time slice or Cauchy slice. In the distant future, I can draw a similar slice up here, constant time slice. And here, there is no horizon at all, and I just see this radiation. And at late times, Hawking showed us that this radiation is thermal, and therefore I can prepare a star, so to say, in a thermal state, in a pure state up here. I can prepare a star in a pure state, but at the end of it, I'm at thermal state, so it's a mixed state. So here I got quantum mechanics, I got a pure state evolving into a mixed state, and that seems like a breakdown of fundamental quantum mechanics. The evolution is not unitary. This has been the puzzle for 50 years now. So, in 4 dimension, however, the detailed calculation is available only in the external field approximation. And this is the Hawking effect, which is quantum field theory on the space-time of a collapsing star. So I just have a collapsing star and I have space-time. I don't worry about the fact that the Hawking radiation is going out, and therefore, in fact, the black hole will be shrinking. I just keep the black hole classical. I'm violating energy conservation, but if I just do that, that is called the external field approximation, and Hawking's calculation was in the external field approximation, violating the energy conservation, and then he showed that at late times, the radiation is actually thermal in that approximation. Now, this picture comes up because I'm using conservation of energy, and I'm saying if the black hole is losing mass, then its geometry must be changing. So this is called the back reaction. Back reaction of the radiation on the black hole, and the black hole, therefore, area should shrink. Well, if I say that when extrapolated, this picture is clean, but if you extrapolate it to include the intuitively expected change in the space-time geometry, if the back reaction is included, then the black hole disappears at the end of the process. And therefore, if the incoming state is a vacuum, the outgoing state is a mixed state, which at late times is thermal, and therefore there is apparent loss of unitarity. And the reason is because I got here the initial surface, constant time surface. Here, if I give you the initial data, then we are Einstein's equations, and whatever the theory you have, you will be able to evolve forward. But here, if you give me the information, I cannot evolve forward because some of the information from here fell into this singularity, fell into this horizon, and is not registered here. Again, a much better understanding of this picture comes from this causal structure of Penrose diagram. So here is a Penrose diagram. If I had classical relativity, this part would not exist. This would be just sky plus, this would be sky minus, and this would be the Schwarzschild black hole, which is outside. If it is a spherical star, there will be Schwarzschild black hole here. But now the mass of the black hole is shrinking, and therefore the singularity, so to say, is becoming weaker and weaker, because the wild curvature goes like mass upon R cube. And so therefore the mass is shrinking, and therefore this singularity is getting weaker in that sense, and finally the mass will go to 0. So the heuristically, this is the kind of picture that you would expect, and this is a picture that Hawking drew in his 74 diagram. This picture has no calculational basis. This is an intuitive picture that you expect from energy conservation. So in this picture, then when the black hole is gone, I don't have a singularity, and I just have kind of nearly flat space. That space-time, the future up here. And here is the initial surface. This is like the t equal to the in surface. And here is the future surface. This is out surface. And here you see clearly, I can have some initial data here. I evolve, some of it falls here, some of it goes out to infinity. So only part of the information is available here. So I cannot take that part of the information and evolve back and hope to get back the initial data that I got here, because I lost something here. If I took this as well as what happened on the horizon, I would be able to reconstruct, but we don't do that. If I just look at this surface, which is like looking at time t equal to 0, time t final, time t out surface, then I would not be able to go. So in 4 dimensions, there is no detailed calculation of this back reaction even today. So this widely used time, but still it is true that this Penrose diagram is widely used, is based on the original heuristics that Hawking had, and it has no kind of no rigorous basis. And Hawking himself changed his mind in 2016 that he concluded that this is not the correct diagram, but the diagram is still used. So this is the black hole evaporation problem, namely that somehow I can have pure state, and then that evolves, and that looks like a mixed state up here, because I had to trace all the degrees of freedom that fell into the horizon. So the usual picture is that I got this in quantum mechanics, I can give myself some initial state up here. That initial state I can evolve. Some of the modes, there is always, because the geometry, there will be creation of, there will be pairs of modes that are created. One of the modes falls in, modes of the field, and another one goes out to infinity. And therefore, what goes out to infinity is correlated to what fell in. And I have access only to what happens to infinity. So I lose these correlations, and therefore I got apparent loss of information. Now this is something that can be really rigorously studied in some simplified models in 2 dimensions. In other words, RT plane. It's like Schwarzschild, but it's slightly simplified. Okay, it is not general relativity, it is some other theory, but we just do it because it is mathematically simpler. And it's called the Callan-Giddings-Harvey-Strominger model. And in this case, one can actually calculate the back reaction, and this is something that was done with numerical relativist Franz Pretorius and Fethi Ramanazoglu, who was his student, and Amos Ori has done some analytical calculations as well. So in this case, again, I got some shell, like Vaidya-like shell, for falling and making a black hole. This, by the way, those who teach general relativity, Tarun teaches, this is an excellent model, because in one lecture you can actually do collapse to form a black hole classically. And you see everything happening in front of you. And so this is a very nice lecture, because you can just do it analytically, everything. Okay. So it's a simple model up here. But then again, because of quantum evaporation, the black hole actually evaporates. So here is the dynamical horizon that forms. And finally, as soon as, because of matter, it's like the Vaidya solution, dynamical horizon forms. It is space-like in this region. It's not well drawn for that reason. But over here, it is time-like, and it shrinks. And what I've done here is to just look at the semi-classical region. So I'm really not looking at in the future up here. And the statement is that in this case, you can check that the singularity is actually tamed by the back reaction. The metric is actually continuous there, and the metric can be continued, therefore, across this space-time. And furthermore, the singularity stays well away from the infinity up here. It was believed that there are, Hawking, in fact, and Stewart had said that in this case, there will be a thunderbolt singularity which will go out here. We check explicitly, the metric is completely tame here. You can continue it in this region. It is just because the Stewart's numerical program was not sufficiently accurate. There is no firewalls that people have talked about here in this model, and the metric is completely smooth up here. And what forms is really a dynamical horizon, and what evaporates here is dynamical horizon. Here the area grows, and here the area shrinks up here. And in this whole picture, in the semi-classical picture, certainly there is no event horizon, but even in what is expected, from making some assumptions which seem physically reasonable, Madhavan here and Victor Tavares and I have shown that in fact in the full final picture we expect in the quantum space-time, we expect there to be no event horizon either. So this is just to give you some feeling that the picture is not so simple up here, that you may not have any event horizon. Here you got this event horizon, but that assumption may not be really realistic in the full case. So now the last slide about technical part of the talk, which is really what happens in 4 dimensions. So what I'm going to talk about here is just a semi-classical regime. And I'm going to consider this situation. Supposing I got a collapse and a stellar mass black hole forms. And supposing this, after that, nothing falls into the black hole, right? A stellar mass black hole is formed. Then it evaporates. And supposing we wait until it shrinks down to lunar mass. Now, you'll all agree that lunar mass is still large because it's an astronomical object, right? I mean, we landed on the moon, so it's clearly not a quantum object, it's an astronomical object up here. But still, the mass of the moon is only about 10 to the minus 7, 1/10 millionth of the mass of the sun. Therefore, this process actually takes extremely long time. But you expect that this is a really simple process in which nothing very serious should happen. Semi-classical approximation should hold. And the question is, what happens? Well, this process actually lasts for some 10 to the 64 years. And in this long time, it's huge time, right? I mean, our history of the, compared to the cosmic history, it's a huge time. And during this time, a large number of these Hawking pairs are created, and one of them goes out to infinity and one of them falls into the horizon. Again, here is a picture where I got sky minus, where I got some shell falling in, null shell falling in, forming a singularity. There's a dynamical horizon which is space-like and grows, and then classically it will just stop here and join on to an event horizon like that. But quantum mechanically, there is a radiation, so it becomes time-like and it becomes like that. And I'm just getting the space-time here when the mass is lunar mass, and I just want to know what happens in this part of space-time. Now, but the statement is that because the incoming state here, actually we can consider incoming state to be pure. I can just take a coherent state here. That's what we did in this CGHS analysis that I just mentioned up here. We just took a coherent state, quantum coherent state of scalar field. So we can do the same thing up here. So therefore, I can take a pure state up here, and then the statement is the state is pure here, the state is pure here, but the correlation, but the outgoing modes are correlated with the ingoing modes up here. That's the statement. Okay, so these are the correlation. Now there is apparent information paradox even in this semi-classical space-time, and the apparent paradox is the following: that the lunar mass black hole at the end has a radius of about 0.1 millimeter. And the paradox is, how can such a small ball hold so many modes? Heuristically, even if we assume that each mode carries minimum energy, so it has largest wavelength of about 0.1 millimeter, which is the size of the lunar mass, the radius of the lunar mass black hole up here. Even then, you can calculate that the mass will be some 10 to the 22 times the lunar mass. So the problem is basically there are so many correlations, so many modes have gone down, and they are correlated with all these modes up here, and these modes are contained in a ball of just 0.1 millimeter. Now it's not possible for these modes to be contained there. So what happens? So from our point of view, and this is really conservative, and this is a work that is done by several people, that when one solves a semi-classical equation, first of all, you have to have the dynamical horizon. And inside the dynamical horizon, you consider these Cauchy surfaces. These surfaces up here, part of it is outside, part of it is inside the dynamical horizon. And you can look at the dynamics of these Cauchy surfaces up here, inside the dynamical horizon up here, that we got up here. And what one finds is that because of this energy flux here, it turns out that this surface gets extremely stretched. So in the beginning, when a black hole is formed, this surface is only 3 kilometers long. There is the Schwarzschild radius of the black hole up here. But then as time goes on, it becomes extremely elongated. How much elongated? Over 10 to the 64 years, the length here of this surface becomes about 10 to the 62 or 10 to the 64 light years. You might say, why is there a gap? The reason is because these surfaces are not canonical. So one of these figures refers to surfaces on which one of the curvature constants, so-called Kretschmann scalar, is constant, and the other one is the one in which the trace of the extrinsic curvature is constant. So but still, they're comparable to each other. So what happens is that our intuitive idea is that, well, I got this black hole of 1.1 millimeter. I cannot shrink by hand to 0.1 millimeter, but it's really tiny. And how can this ball have so many modes? The statement is that no, this picture is wrong. This is just the mouth of the black hole. The black hole has this long tube, and as time evolves, this long tube gets elongated and elongated to this totally astronomical sizes, 10 to the 64, 10 to 62, 10 to 64 light years. And these modes then become infrared, which is like what happens in inflation. These modes get stretched as the space expands up here. And therefore, they carry very little energy, and then the statement is that it is easy to fit these modes, this huge number of modes that we have got, because they are so much infrared. So the idea is that these modes inside, as time goes on, they become more and more infrared up here, and therefore there is no paradox. You can have those modes still correlated with the ones which are going out. Remember, the question was, how can I have so many modes which went out correlated with this modes contained in this tiny ball? And the resolution is that this tiny ball is not, it doesn't have tiny volume. Its volume is absolutely astronomical, because its length is astronomical, even though its ball up here, the two ends here, if you like, two sphere here and two sphere here, are very, very small. And therefore, when the event horizon is replaced by the dynamical horizon, and you look at the dynamics inside the dynamical horizon, this puzzle really disappears. Okay, let me summarize. So here are event horizons, and here are quasi-local horizons. First, classical general relativity. Event horizons are teleological. One may be forming and growing in the room you are sitting in due to a gravitational collapse a billion years from now, and it's a global notion. We need a full evolution of space-time, and it is not well defined unless space-time is asymptotically flat in the zero cosmological constants case. If the cosmological constant is non-zero, space-time has to be asymptotically de Sitter or anti-de Sitter. For quasi-local horizons, there is no teleology, and there is no dynamical horizon in the room you are sitting in. The quasi-local is a quasi-local notion, does not need sky. And now for black hole mechanics here, for the event horizons, we got zeroth in the first law. The zeroth law is in stationary space-time, and first law is for transition from stationary space-time to a nearby stationary space-time. And the second law is qualitative, is powerful, but it's qualitative, that the area always cannot decrease. Here, the zeroth law requires only isolated horizon. There may be radiation even close to the black hole, but so long as the horizon is isolated, the surface gravity is constant. And the first law is a physical process law. Something may actually fall in, and you can consider finite transition. And the second law is actually quantitative. The change in the area is equal to infalling energy flux, which I cannot say anything like that here. And there are no dynamical horizons in the Minkowski part of Vaidya solution. Dynamical and non-expanding horizons are characterized invariantly by multipoles, and their evolution of non-dynamical horizons provides an invariant characterization of the horizon dynamics, and we have gravitational wave tomography. This is not possible for event horizons because generically, first of all, they are not smooth, and secondly, multiple moments are not available because you don't have any preferred cross sections, two-sphere cross sections, and they cannot be used in numerical relativity, and there is no hope of gravitational wave tomography using event horizons. And finally, what did the Event Horizon telescope see? I showed you this image in the very beginning, the first slide. What did they see? They call it Event Horizon. Did they see Event Horizon? No, I mean what they saw is really a light ring outside a quasi-local horizon and not an event horizon. And here is a picture. Let me just show you this picture up here. Here are three figures. One is a stellar collapse, and here an event horizon falls. Now here, on the other hand, there's a Vaidya collapse and dynamical horizon. Here also dynamical horizon forms and joins onto event horizon. Dynamical horizon forms and it joins onto event horizon. Now suppose I got stellar collapse followed by a Vaidya collapse. Then I got this dynamical horizon. If there had been no Vaidya collapse, then this would be the event horizon. That's why I call it old event horizon, like this one. But because this happened, the area increased. So here is the dynamical horizon again, and that latched on to the new event horizon, which is also an isolated horizon up here. And so what we see up here is that here is the dynamical horizon, here is the dynamical horizon, and the new event horizon is here. Now supposing we are here somewhere, And we are looking at the light ring. What are we looking at light ring of? This object or this object? Well, we are looking light ring of this object, which is not the event horizon of the space-time, but is an isolated horizon, and it remains isolated horizon for 1 billion years, and this is the light ring we are seeing. So we are really looking at the light ring of a quasi-local horizon and not of a dynamic horizon. Now, my friends in Event Horizon Telescope, of course, know this and they agree with it, but they say that, well, we call them Event Horizon Telescope because imagine going to a funding agency or some donor and saying that we want some money for a quasi-local horizon telescope, and it seems like a mouthful and nobody will fund you. And Event Horizon Telescope sounds so beautiful and so nice, and that's why it's called Event Horizon Telescope. Okay, last slide about discussion of quantum gravity. Already in the semi-classical regime, there are apparent paradoxes arise if one takes into account event horizons too seriously, and that led to exotic ideas like the quantum Xerox machines, that was some time ago, then firewalls a little more later, and then fast scrambles and failure of semi-classical gravity in tame regimes well beyond the horizon, even for astrophysical black holes. This paradigm, the last paradigm, has lost its momentum after the LIGO discoveries, where we don't see any deviations from classical general relativity. And we saw that the paradox disappears the paradox in the semi-classical regime disappears when the geometry inside the dynamical horizon is examined carefully. And finally, what happens in the semi-classical theory? And now here, these are expectations. So let me say, suppose the singularity is resolved in a consistent theory, as in many proposals. For example, Hawking's take 2. There was a paper by Hawking, Polk, Strominger. Their Penrose diagrams show no singularity. Then there is no event horizon. What forms and evaporates is just a dynamical horizon. So what happens is that you have got these Hawking modes going out to infinity, and they are correlated with these modes which get extremely stretched. But these extremely stretched modes, if there is no singularity, can pass through this region, and we understand the geometry of this region, which is very beautiful, reasonably well, and they can pass through this region and come out to infinity. And therefore, in fact, these modes which are correlated with the early modes, the correlations will be restored at null infinity and the state will be pure. What we don't have yet control on is this little region up here, because here the modes are extremely infrared, extremely long wavelength, whereas here towards the end of the evaporation process the modes are very ultraviolet. And how the two things match on to each other is not understood at all in the approach that we all follow, that loop quantum gravity people follow, and that is the open problem at all. So it's still under debate, and maybe we cannot do it, and therefore the picture is completely different. But at the moment, the hope is that we can actually fill this picture. Thank you.
So thanks, Abhay, for a wonderful talk, and we can have questions now.
That's all.
Super.
I had many questions about this last picture, but I'll ask the main one.
Yeah.
To set up this picture, did one need to promote the Hawking computation that the radiation is thermal to an exact statement in that it's really thermal even when one includes e to the minus s effects? Or said another way, did one need to assume that in this picture here that the classical no-head theorem is really exact in the quantum theory? If one looks at the metric and fluctuations of the metric and so on, they really have no information about the infalling matter except for the total mass, charge, and angular momentum, because that seemed to be implicit in.
Yeah, no, I don't think so. I think we don't need to assume that the radiation is really thermal. In fact, in the CGHS model, we found that towards the end it is not thermal, and there are some deviations from thermality. But of course, CGHS has its own peculiarity, so we cannot conclude completely. So no, I don't think it's just that the correlations are restored is the only question.
Yeah, no, sorry, maybe let me say it another way. The statement seemed to be that at least till the black hole becomes lunar size, and beyond that, as you say, you may not know, that no information is present in the radiation that emerges till then. And so did one, whether it's thermal or not is a separate question, but the facts seem to be that there are correlations between outside and inside, but not correlations between outside and outside.
Right.
And so did one need to assume some extension of the no-head theorem to the quantum theory for that, or does it just follow in some?
I think that it is certainly true that there's a conservative assumption that is made, but it's not essential for the anomaly, for the analysis. The only essential part is that that the total correlation, the total state is pure. That is the only thing. So there could be correlation between outside and also outside and inside, but the total state is pure is the only thing that is being assumed really. Rajaram, you have
Abhay, one encounters the statement in textbooks and so on that there is no expression for energy or energy momentum of pure gravity in general relativity, but you had an expression up there. So
wonderful,
sure,
wonderful.
yeah.
Thank you so much. So this was one of the most beautiful thing interplay between geometry and physics I saw. Thank you for asking that because it's really beautiful. Yeah. So the statement is that so the question is the following. Just let me paraphrase the question. That in general relativity, you are got a stress energy tensor for everything, right? You are got for matter, but there is no stress energy tensor for the gravitational field itself. Now people, starting from Lifshitz and other people, write down this so-called pseudo tensor, which is supposed to represent, something like energy momentum in the gravitational field, and then they use they use it for certain calculations. But it's a coordinate dependent statement, and there's no coordinate independent statement. So Rajaram's question is that, well, but here is a statement which I said is geometric and is coordinate independent, and this is really the flux of energy carried by gravitational waves in a strong field regime. It's not null infinity, but strong field regime. And this was a shock to me for the same reason that you see first. It is true only when you have got a dynamical horizon. If I draw a surface slightly outside or even slightly inside, the slightly inside was surprising to me also. The slightly outside was not. This formula completely breaks down. So somehow there is something very beautiful interplay between geometry and physics, that this formula holds exactly on the dynamical horizon but does not hold on any other surface. So I don't know what the flux of energy momentum would be through this room, for example, because we are not in a dynamical horizon situation, but I do have it on that surface, which is, it was one of the most beautiful interplay between geometry and physics I have seen. Yeah. I would like some students to ask some questions. There may be naive questions, that's fine, but you should ask questions. Okay? Okay, somebody.
Yeah, I'll pretend to be a student. Just a quick question, which is, what are the energy conditions that you use for these black hole mechanics laws for the dynamical horizons? Yeah.
So the energy condition, that depends on various results. Several results go through with just the null energy condition, but for all the results, particularly this formula that I have written down up here, for that to go through, you can switch on the light. That one needs to know that the matter has a property that if I take TAB and LA, this is not, it's like the weak form of dominant energy condition. This minus that is a future causal vector. The dominant energy condition would say that this is true for every, this true only just for this one L vector that we got, the preferred L vector whose expansion is 0, not for every vector, is a future directed. So that's the condition that is used. As you can see it from here, because TAB times LA. So if this is future directed causal vector, minus that is a future directed causal vector, is dot product with here will be positive. So because this is time-like vector. This is a time-like vector normal to the space-like. So that's why it's used.
I have a question.
Yes.
So in the beginning you mentioned about some teleological issues with the event horizons.
Right.
So let us say in the distant future, if a shock wave just collapses to form a black hole, we just saw in the diagram that this dynamical horizon, its area increases along the space-like direction, not time-like or null direction. So still in this prescription also, if there's a shock wave collapse in the distant future, we will still be inside the event horizon. So
no, it's an isolated horizon. It won't be event horizon. It will be an isolated horizon. So the statement would be that if in fact the shock wave would be that you reduce it further and further and further. So this dynamical horizon, already it is quite little, but this dynamical horizon will be instantaneous and then join on to this this isolated horizon in the distant future. You can draw the event horizon, but the event horizon is not quasi-local. What you will get is still a dynamical horizon joining onto isolated horizon. So this part, and this part is all quasi-local horizons. This is dynamical, this is isolated. To interpret as an event horizon, so, and this is just local properties because it is null and the expansion vanishes here. This is space-like and its expansion vanishes here. That's all that I'm using. I'm not looking at the global things like what is the shadow of sky and such things. That is event horizon. So, okay. Did I answer your question or you still have something else?
You answered it, but my original question was, so okay, the idea is to go from the global definition to local definition, right?
Quasi-local. I say quasi-local because you still have this expansion has to vanish on the whole two sphere. It's not at a point, but on the whole two sphere. Marginally trapped surface is a two sphere notion, and that's the only reason the word quasi is used. It's on the entire two sphere rather than at a point.
Okay. One more question actually.
Please.
So you also talked about the correlation between the modes that fall inside the black hole and the ones we observe in the gravitational wave signal. So you said that it is not well understood why is the correlation. Is that true or it is
No,
well understood?
that is understood. What is not well understood is really the very end point of this evaporation process, and that is what we don't understand well. So in this language, I guess I should just use this. What is not well understood is what happens in this region up here. How is it that this extremely long wavelength modes, they are correlated with these modes, but then with these early modes which were emitted here. But exactly how they are meshed on to the long wavelength modes and the short wavelength modes, how they are meshed on, what exactly is the geometry, space-time geometry in this region, that is what we don't understand. On any one surface, everybody agrees that the modes which are outside are correlated with the modes which are inside. And as Subra said, it could be that there is a correlation between even among the modes which are outside by themselves. But the total state is pure, and therefore there are correlations between what is happening inside and what is happening outside is accepted by everybody, and we understand that very well. What we don't know is really this region of space-time, the end of black hole evaporation. So there's a dynamic, the horizon is shrinking, and it becomes Planck size here, and then what happens to this future up here is what we don't know.
Yes, I have a very naive question, so I can just pretend to be a student.
No, the naive questions are the most difficult ones.
So I just saw this number, you had this 10 to the power 64 years.
Oh.
So that looks very large by any standard. So is it relevant for any like a real systems, that number? No, I mean like
it is large by any standard.
Right. So therefore that theory, would it be relevant for any like a physical universe or
yeah, I think it is. I mean, that's because, if you think about the physical universe being, let's take this model that we have today. There is a quote unquote, the energy budget is the one that, the Planck data tells us, and therefore almost 70% of it is in the cosmological constant or dark energy. Suppose dark energy is just cosmological constant, then the universe will evolve to infinite time in the future.
Okay.
And then slowly the universe will become very, very cold, and it will evolve in infinite time in the future. So these are conceptual questions. Questions of black hole evaporation are not questions about what is going to happen up to now in our universe, unless the black holes are very, very small. But for macroscopic black holes, I'm considering these are only conceptual questions. These are not.
I mean, like the question I'm asking, like I can ask a similar question, like, okay, what is the probability that all the gas molecules just collapse to me? And there's a finite probability, very small, right? But we know that this doesn't happen because of the second law, and which essentially says that probability is very small, right? I mean, in that sense, my question was like, is it relevant? I mean, in that sense.
Yeah, so the statement is basically that one is looking at the idealized universe. So in the real universe, you will not have an isolated black hole, which is just sitting there and radiating and nothing else is happening, something. So these are thought experiments which are good to sort of, to analyze and see what happens. And the whole information loss paradox is, for macroscopic black holes at least, is really in the realm of thought experiments. It's not about, it ignores, it's an idealized experiment. So,
Thank you.
Saurabh?
So I just wanted to add one comment to that. Of course, as you say, it's a thought experiment and it's important for making quantum mechanics and gravity consistent. But nothing prevents much smaller black holes from existing than astrophysical black holes. If you take a black hole of mass 500 tons, which we don't know how to form, but let's say, it could form, it would evaporate in about 5 seconds. So it's not that, all black holes take 10 to the 64 years. That figures for solar mass black hole.
Yeah. So
you can have much smaller
this
black
64 really refers to the astrophysics, solar mass, lunar mass black holes, not the, and there could have been black holes which have formed, the small ones in the primordial, during inflation. People work on this quite a lot, and so we would like to know what happens to them as well. There's a question there.
Sadiq?
So when we are talking about evaporation of a black hole, precisely what, mass is converting to energy. And there is some equilibrium which is sought because of some temperature difference between a bath and the black hole. Am I okay so far or not really?
No, this is not equilibrium, because a black hole is actually, as it shrinks, it becomes hotter and hotter.
Right. Actually, I was coming to that. Actually, so my question is, what precisely is evaporating in terms of the mass? Are we looking at particulate mass? Are we looking at some infinitesimal mass in getting lost in infinitesimal time? And so it's a very theoretical concept, or are we looking at the kind of mass which is falling into the black hole and making it a black hole in the first place?
Yeah, so it's kind of mass, but it's all the particles, known particles will be radiated away. It's standard particles. They will
right.
be,
so we are
everything
assuming,
that couples to gravity and that exists in nature will be in the radiation.
So one assumes that the identity of the fundamental particles which are falling into a black hole persists on the other side of the. Is that an assumption that one makes, or what is?
Okay. In curved, so this is my point of view. In curved space-time, one really cannot talk about particles. The notion of particles doesn't make sense in curved space-times in general, because there is time-dependent geometry, and so in curved space-time we can talk about fields and we can talk about field modes. So it's not a big deal, but I can talk about field modes of a Maxwell field or field modes of a Dirac field and so on and so forth. So I can talk about that. So the statement is that, yeah, these modes do exist. I can talk about them inside the dynamical horizon. So in our picture, what is happening is really the dynamical horizon is shrinking continuously. And there is an invariantly defined mass and angular momentum for the dynamical horizon, and that is changing in time in response to this radiation. So far, I would say almost maybe every calculation really looks at non-rotating black holes. There may be just a set of measures, 0 calculations will look at rotating black holes. So these are kind of considered to be spherical symmetric, so it's only the mass, not angular momentum. But that is a well-defined concept for a dynamical horizon. And then the statement is that it's actually mass is shrinking due to this radiation which is going out. And in this model where one can do detailed calculation, there is something very beautiful which I found very attractive. Namely, one can actually correlate the mass of this dynamical horizon with the mass defined at infinity. For technically, people who call it the Bondi mass, we can correlate this mass completely. There is no so there is a notion of mass that is defined, and that mass is actually getting lost. So is that okay, or do you have some other questions? You can also ask me later. Especially since everybody is trapped because of rain.
Tarun has a question.
No, it's more like a clarification. At some point you said this is like inflation.
Like inflation.
Right. You're kind of stretching the modes to, basically populating k tending to 0 modes. And so is there a similar analogous problem with this, this area that you pointed out in your problem? Because people keep talking about this post-Transplanckian issue in inflation. Is it similar, or is it?
No, these are infrared, okay. So I don't have any problem with things are getting longer. Okay, the Transplanckian problem in inflation, right? So the Transplanckian problem in inflation has to do with, if I take these modes, which are observable modes, and if I go back and back and back in time, then they will become shorter and shorter, because here we're never going back in time. I mean, in the early stages of the evaporation, the modes are, there's a Schwarzschild black hole with a 3-kilometer radius, and these Cauchy surfaces are the standard ones that we know about. They're also some kilometer long. These modes are just normal modes up here. So, and we never go beyond that, because that was what was happening in the beginning. So there is no analog of inflation. I feel like there is no singularity in the past. There's singularity in the future. There's no singularity in the past here. So, and when you go in future, the modes are just elongated and not.
Thanks.
So any more questions? I saw people in the back row, but I don't know whether you were stretching or, oh, Rohini is here.
Yeah, Rohini is here.
This is going to be very, very stupid, but what I thought was that when you are describing this coordinate independent description, so the simplicity that seems to appear in the interpretation, somehow it looked to me like making use of gauge invariance, and sometimes I understand the physical part of the phenomenon, and the unphysical things somehow being gauge dependent go away. Is that something that's a correct interpretation?
That's a correct interpretation.
Okay.
But the question was about how do you, because the diffeomorphism freedom is a little more complicated than the internal gauge freedom. So how do you get to that was the only question.
But I wanted to know whether conceptually I have understood it right.
Yes, that's exactly right. How do I get? So these numbers are just gauge invariant. You can compute them. Sumati can compute them. You would agree that they are exactly the same, because they're just numbers.
So it is just like, for example, in my ordinary field stuff that I do, ordinary electromagnetism, I will come across, sometimes if I do calculations in two different gauges, and in some gauges they just look weird.
Yeah.
And that weirdness is somehow removed, and only the things that are of physical significance are abstracted.
That's exactly right. Okay. That's exactly what is happening.
Okay, thanks.
Yeah, so again, a very nice question. And so initially the paradox.
Abhishek, can you hold it nearer to you?
Yeah, okay. Can you hear now?
Yeah.
Okay, so again, a very nice question. I mean, so initially the paradox seemed to be that a pure state goes to a mixed state, but this is through a semi-classical calculation. So of course, one could just say that it's a wrong calculation. If one did a proper quantum calculation, there would be no paradox, right? So finally, at the end of the day, is it clear what's going on?
No, it's not. So that's exactly right. What you said is exactly right, that we want to do the real quantum calculation and say that there is no paradox, but we don't know how to do it yet, the full quantum calculation, because it requires full quantum gravity, and we don't have a full quantum theory of gravity. What we do have is something like what happens in semi-classical regime, and so there we can still ask the question. That's why I focused on that particular question, because it could be asked already in the semi-classical regime. And so if we have, so any complete theory of quantum gravity should answer this question. It could be that there really is no unitarity, and in fact that was what Hawking's first viewpoint was in the 70s, that unitarity is not there, and therefore you really have what you call a generalized metric, generalized operator, which will map density matrices to density matrices and what properties it should have, etc. But this operator could allow pure states to evolve into mixed states. So why do people think like that? Well, let me just say one more thing, and please continue to ask me. Why do people think like that? Because the statement is really the following, that if I consider this, what happened up here, this is the Hawking's heuristic picture, expectation picture. This picture has no rigorous basis, but the picture up here is that, well, there is a singularity here. Okay? So it could be that, in fact, when the singularity is resolved, you go off in another universe which is not causally related to this universe, our universe. And so some information stays in our universe, some information goes into a causally disconnected universe. People, serious people, consider such possibilities. Then unitarity is there, but it's there if you consider all possible universes, so to say. But it's not in any one connected part of our universe up here. So these are called baby universes, and they can take away universes. I personally feel that doesn't happen, but that's not, I mean, we don't have full quantum gravity theory, but in order to work towards the answer, you had to have prejudices, because otherwise you would not make any calculations or any progress. And so my personal feeling is that no, once we have full quantum gravity, we will clearly understand. And in our picture, if what is open is really this region up here, we understand the geometry in this region, what is happening here, then we will have a clear understanding that, singularity is resolved and the information comes out, and it just takes a very long time for it to come out, and that's life. And it's like burning a piece of coal, There's the usual analogy people take, I light a coal, and then instantaneously, suppose the coal was in a ground state, so it's a very simple state, and then it radiates, so this thermal radiation goes out for a long time, but the total state is pure, so therefore there are correlations between the coal and what went out. Then the coal sort of bursts down, and the ashes finally will go to zero temperature, and then the statement will be that there will be actually complete correlation. Correlations will be restored because it's a simple thing up here. It just takes very, very long time, because ultimately when the coal is quite cold, there will be infrared modes, and these late time infrared modes will be connected with the early times hot modes that came out. There's a complete correlation, and there will be no paradox. So something like that would happen here is our view.
No, actually continuing on the kind of thing that Abhishek brought up. So from a statistical mechanical point of view, you do have an analogous situation where you have an underlying microscopic dynamics which is completely reversible, and at the coarse grain level you arrive at irreversibility. Or, for example, quantum to classical transition via decoherence, where you ignore certain degrees of freedom, and this irreversibility is a consequence of that. So, would one consider it to be something like that, lack of information? I mean, if you do the full quantum calculation, you restore unitarity. That would be like analogous to tracking every particle and restoring.
Yeah, but the statement is here that, I mean, one wants to understand at a fundamental level. The whole problem is not, there's no direct analog of, I mean, there's no direct analog of the statistical mechanical kind of description, if you like. I mean, one wants to understand the problem at a fundamental level, as you said before. But then, in the case of the gas or in the case of statistical mechanics, one knows that at the fundamental level there is no loss of unitarity or loss of. But here we don't know. That's the key. Even at a fundamental level, here we don't know. Without going into statistical mechanics description, and our challenge is to get that, right? The challenge is to arrive at a microscopic description, at a fundamental degrees of freedom description, and show that there is no problem, or show that there is a problem, one way or the other.
Hello, sir. Apologies if it is slightly off topic, but I was curious about the effect of accretion or the rotation speed of black hole on this horizon radius. Because I read about this thought experiments that
hold it closer.
For the maximally spinning black holes, there is a Kerr limit of 0.998. So it can lead to naked singularity if the spin speed goes above it. And I was curious, like, if accretion can add to the angular momentum of a black hole, right? If the black hole is accreting along its spinning direction.
So there are many detailed calculations that were done, and at one stage it looked like if you just take into account the first order perturbation theory, then maybe it was possible to overspin the black hole or overcharge the black hole. But then it was shown that if you take into account that is just an approximation, and you should also go to second order, and when you go to second order, then you cannot. So I think that so far there is no mechanism which has survived to overspin the black hole or to overcharge a black hole to make it into a naked singularity. Okay.
Okay, so are there any more questions from back row at all? No? Okay, so thanks a lot. Let's thank Abhay again for a wonderful talk. And I'd like to invite our director to present Abhay with a memento.
Oh. Thank you very much. Okay.